Let's get started. So look, so when we started, had this idea of creating the Distinguished Energy Seminar Series, our thought was to recognize people in the community that were actually, on the front lines in terms of providing the innovation and technology leadership to get us to a state where we can realistically lower humanity's carbon footprint. The other side of the coin was to expose you to the sort of movers and shakers in the field who are actually, by their actions, getting us ever so closely to the goal of lowering humanity's carbon footprint in a context that was affordable. Yet-Ming Chiang is unusual in pretty much every respect, in that he's not just a creative thinker, but an innovator and an entrepreneur, someone who is well known for taking problems from the laboratory into the market and doing it serially. I think he's already done it, 6 times, if my count is right, with 2 very exciting families of technologies targeted in different sectors of energy storage. Now he's at MIT, as many of you know. He's the Kyocera Chair in Material Science and Engineering. Did, I think, pretty much all of his education was done at MIT. Has received all the honors you could imagine for someone of his caliber and reputation.
Not all of them.
He could always use more, right? But he is a member of the National Academy of Engineering, which is the highest distinction that an engineer can receive in the United States. He is also a fellow of the American Materials Research Society, as well as a fellow of the American Ceramics Society, and a fellow of the Academy of Inventors. I got to know Yet-Ming as we often do, primarily through his papers. And I always felt that there was a certain ability to innovate at a small scale with a sort of full and I think winning knowledge of what it takes to translate small-scale discoveries into valuable products. And I believe today he'll give us 2 bits of treats, 2 examples of stuff that he's done in his own career. And I look forward to joining, hopefully, as many of you as possible in the lunch meeting to follow, which is in 216 Holden Hall in this very same building, where we'll get a chance to basically probe Yet-Ming and the energy storage themes that he's going to talk about, but also perhaps in the metal printing theme that he's also been quite influential. So without any further ado, let's welcome him to Cornell.
Thank you. Thank you, Lyndon. Can you all hear me? I am mic'd up for the video, but am I also mic'd up for the room? Okay, yeah, let's see. Maybe I should wear dual mics.
How is the lighting? Is the light good, or you need?
No, that's fine for me. Yeah. There. Do this with a mic on either side. Is that better? Yeah. Okay. Better. Okay. So I understand. So first of all, at the bottom here, a bunch of logos that represent folks I've worked with and gotten either intellectual stimulation collaboration with, or in some cases they gave us money. Right. So I'll touch on a number of these collaborations as I go along. I understand that this is also a class. Yes. Right. This is a class. So who is here that has to be here because they're a student in the class? Am I okay? All right. Okay, a bunch. All right. So being a class, I'm going to start with a quiz. This is you see this fellow there in the red Cornell red shirt? All right, this is a quiz. Who is this person between me and my son? Does anyone know? He's obviously from Cornell. All right. Here's the hint. All right. One of the things I do in my spare time is to coach youth wrestling. Anyone? Does that help? No. You're all spending way too much time in the lab. That's Kyle Dake, your 4-time NCAA champion, who is now getting ready for the Olympics. Right? All right.
We can tell he's a wrestler, though.
That's right. Just look at him, right? And I have to say, when Lyndon sent me the email inviting me to give this lecture and listing several dates, the first thing I did was to go to the Cornell Wrestling website and try to match those up against the home matches. It's my great disappointment that I found that none of those dates coincided with a home match.
Better next time.
All right. Okay. All right. So almost I would say everything I work on today, I'm in the material science and engineering department, but all I work on are things related to climate and energy. And so, when students come to visit and say, that's all I work on, if you're not interested in that, there's no reason to be here. We can end our conversation now. But this is a slide which the source is at the bottom, but I took this from the Breakthrough Energy website. About where greenhouse gas emissions come from today. And I wanted to use this to say that, here are the parts I've been working on. Transportation, batteries for electric vehicles, I've been working on those, I'd say, since the late 1990s or so. And we continue to do a lot with that today. I'm not going to say very much about batteries that are focused towards high energy density for transportation. I've already had a couple of conversations with people about that. We have quite a bit of work in that area. One of the interesting new applications we're thinking about is electric aviation. Is it real? Is it going to happen? And so we can talk about that separately, but I'll skip over that today. Electricity systems, I will talk about that. So electricity and heat production, but mainly electricity. And a number of years ago, we developed lithium-ion batteries based on lithium iron phosphate that were the first large-scale grid storage lithium-ion batteries. And this is one of those installations. At that time, this was the largest lithium-ion battery farm in the world. And this is coupled to a wind farm in West Virginia. And then I'll talk about low-cost storage today, and I'll explain why. And recently I've become more and more interested in electrochemistry for industrial production, and you see in my abstract, I'm going to say something about cement. Right? Cement is a fascinating material. This ugly gray stuff is just fascinating. Right? And especially, I have a strong sense that we're on the cusp of innovation in how to deal with cement. Right? I'm going to give you one example, and I'm sure there'll be a lot of others. You see agriculture in this corner here and say, well, I haven't figured out how to do anything related to agriculture in my professional life, but in my personal life, we raise chickens, right? And so this is, mainly my wife does this, but she raises up to 300 chickens a year for market, right? And this is how we do it. These are the most expensive chickens sold in the state of Massachusetts, right? They show up in high-end restaurants, right? And they're raised with all the care that you'd expect 2 PhD engineers to apply, right? And so we try to live this sustainable life as well as the professional life in climate and energy. So I have 11.5 kilowatts of PV on the roof. I have geothermal heating and cooling, raised chickens, raised bees. We just made some maple syrup. I know it's too cold up here for the maple sap to run, but Massachusetts is a little bit warmer. So just collected about 20 gallons of maple sap over the last couple of days. And so this is what I do with in my life. I try to live the sustainable life as well as to do research on it. Right? That plus wrestling. Right? Okay, so this is the backdrop. And what I wanted to talk about today, as the abstract says, is what can we do in the face of this remarkable declining cost of electricity? Right? The lowest cost electricity in the world today is renewable. Right? And it has just this one big problem, which is the fact that it's intermittent. Right? And so I think all of you have probably at one time or another seen a plot like this, but you see that these are PPAs, power purchase agreements, and they're now dropping below that of gas. Right? And so 1.5 cents a kilowatt hour is widely available, for instance, in Texas, right? But also in Texas, periodically for, say, a day a year or a couple of days a year, that price might, or even hours, might spike up to $9,000 a kilowatt hour. And that's an illustration of occasionally things go haywire where there's very high demand and suddenly the supply dries up, right? And so, intermittency of this kind, I'm going to spend a fair amount of time talking about intermittency over longer periods. And so on the right is a monthly variation, on the left is a monthly variation. On the right is still a daily variation, but it's over more hours than you might think. So it's not just the so-called duck curve, the ramping that you've probably heard about, where you need to accommodate a few hours in the early evening, right? So durations go longer than that, right? So the first topic is going to be this topic of storage. This is a nice illustration of the fact that we don't do very much storage today, right? So storage is that little gray circle there. The majority of it in the world today is pumped hydroelectric storage. Batteries are this tiny part, right? And so we must have a sense that batteries will grow, or else we wouldn't be spending all this time on it. And so if we look at this, why is it that we think storage has a future, a growth curve that's going to be steep in the future? And I wanted to use this slide, which is a plot of data taken from from the EIA site there. What this shows is generation, so how we produce electricity since 2001 is shown here, right? And what you see here is that coal is steadily decreasing, right? And the reason it's decreasing, it doesn't have much to do with actually renewable electricity. It mostly has to do with natural gas, right? And so you see natural gas is increasing, and actually on this plot, the only thing that's increasing is natural gas and renewables. Right? Nuclear is roughly flat. I think that it would be wonderful if in the future nuclear takes a huge upswing, right? But in the near future, it's relatively flat. Hydroelectric power is flat, right? And so renewables, however, are a factor of 5 less than natural gas. And so you come, if we were to try to distill something, just a very simple statement, that our goal is to beat natural gas. Right? And Lyndon referred to the fact that we try to find simple problems. So I try to find really simple statements and really simple problems that we can work on and get our heads around. And whenever I talk to economists, they always tell me, oh, it's much more complicated than that. And I say, oh, no, but that's not going to help me. I need to have a simple thesis I can actually glom onto and work on. And so let's beat natural gas. Right? So can we beat natural gas? And in order to do that, renewables, we need some kind of a breakthrough in storage so that we can take that renewables growth curve and beat natural gas. Right? And so mostly the storage being installed today for the grid is lithium-ion batteries. Right? And so this is through the second half of 2018. But you see that the big blue part, this is grid storage alone, no transportation here. And so what we're installing today is lithium-ion batteries. And the cost curve has come down a great deal, and that has a lot to do with that. And so a natural question, when people very often ask me, and which I'll try to answer today, is, so is that it? How far can we go with lithium-ion batteries? What can they do for us? Right? And so I'll get to that. And I referred to earlier this installation. This is West Virginia, Laurel Mountain. Right? And the early applications of lithium-ion, and today we're still in the early stage of grid storage. So early applications of lithium-ion are relatively short duration, meaning it's just a few hours. Right? And so the duck curve over here, which I refer to, I think probably everybody is familiar with, is how it shows you how the generation is mismatched with the increase in demand at the end of the day in California, and therefore you need, the idea behind storage is to supply that, to accommodate that ramp. And in fact, that was the purpose of this battery farm. It was that when to supply the electricity from those windmills to the grid, relatively weak grid in that area, this was for a ramping application. Right? So, so what we do with storage, there's a cost factor to it, and then there's a duration factor to it. And it turns out that the longer the duration we use it over, the lower cost the battery has to be, right? And the reason for that, there are a number of ways to explain that, and I'm going to try to show you a couple of ways to do it. So this is a plot which some people have told me is too complicated. If you think this is complicated, wait till you see the next one. Right? But what it shows you is on a log scale, the capital cost of the battery. How much does that battery cost to build, to install, as the installed cost? And if we assume that that battery lasts us 20 years, right, and we apply a discount rate, but mainly the thing is that it's an asset with a fixed lifetime, so we only get to use it for 20 years. Right? If you think of the battery as just a power source, it's really a bidirectional power source. We store some electricity, but its function is to deliver electricity. Right? So think of it as a power source that delivers electricity, and we ask the question, what is the cost of that delivered electricity? Here you have 15 cents a kilowatt hour top line, which I understand is roughly the retail price of electricity in this region. Right? And so the capital costs and the number of cycles per year over those 20 years determines the cost of delivered electricity. And so the goal of the storage is to make that delivered cost as low as possible, and in our case, to combine it with renewable generation cost and come out less than natural gas. Right? And so you very quickly see that as you use it less and less frequently, if the need is to use it less frequently, then the capital cost has to be much lower in order to have the same cost of delivered electricity. And then these colored bars are just different applications. There are a number of grid applications over on the left. And then you can go all the way out to seasonal storage of, over a whole year, which is essentially what hydroelectric power is. It's seasonal storage, frozen water that then runs. Right? And so I can tell you that if you look at this, there is no electrical chemistry today that at system level, I can imagine getting to $1 a kilowatt hour. Okay, so I would say that we don't really have a seasonal storage solution, but we do have developing solutions that are in the middle there. So the problem with this plot is that cycles per year is an oversimplification because no battery simply just runs up and runs down. And that's one of the problems in the lab. We go in the lab and we cycle batteries like this, and then we get out into the real world and they don't do that. Right? And so you can think of different ways to add all these different nuances. And so this is the complicated version of that plot. And so there's a couple of footnotes here. We take that to normalized cycles per year, which means we take there's a power capacity factor and a rate of power. So forget all that, right? So this is just a way of actually normalizing to what you actually, the way you actually use a battery. So we can have a more complicated version of that plot. But the real purpose of this plot is to show you where different battery technologies are on this cost curve. And so lithium-ion batteries, I plot them as relatively insensitive to cycles per year because you're constrained in the design. A battery is a battery. You can cycle a lot, you can cycle little. It's roughly still the same battery with still the same cost. Right? And so even if we use it infrequently, its cost doesn't change very much. But then we have things with curves on here which represent flow batteries, for example. And a flow battery, you have the ability to change the chemical storage tanks, the size of those relative to the stack. And so you have a power to energy ratio that you can change. And as you go to longer duration, what you do is build less stack, build a larger tank. And if those are low cost chemicals, then the cost of the whole system comes down. And that's why those curves might come down, right? But, and then there's something on here called aqueous future redox flow battery, and that's something I'll talk about a little bit, right? So this is one way to look at the cost requirement. And then the next thing I want to do is to spend a few slides talking about actual use cases and what kind of. So on this plot, where are we in particular use cases? And I'm going to use some work that we published recently, a study we did with Jessica Transick at MIT. And the idea was to do the following. You have renewable generation, and you have a couple to storage, and you're trying to deliver electricity. The question is, what electricity are you trying to deliver? And this stack shows that there are different types of power plants. And so something called a natural gas peaker, you can think of it as a 4-hour block of electricity that's delivered. And maybe you do it actually twice a day. So you have something called a bi-peaker, right? Then you have something called intermediate generation, roughly 8 hours. Then there's base load, which has to run 24/7. Right? And so as an academic study, we can use very simple power profiles. Let me just show you those in a second. The idea is to take this, okay, couple it to renewable generation. Here are the very simple output profiles that we used in this work. And the question is, if we take that storage plus generation together, and we do a lot of optimization, find the cost minimums for that, what does it tell us about the battery we need? So baseload is just flat. These are all just square waves, or either flat or a square wave. So this is vastly oversimplified, as might be appropriate for an initial academic study. Right? What do you do at a professional level? So I have friends at a company called Forum Energy who do this at a level where they actually are contracted to do this for customers, this kind of analysis. And what is really different is the fact that these output profiles are not so much these simple square waves, but what a power plant in a given location in a country or a region is delivering to customers. And that'll be a much more nuanced and much more complex profile. Right? But the process that one goes through in order to understand the storage needs is similar in both cases. So for example, these 4 X's represent Arizona solar, right? Lousy wind, really good solar. Texas, good wind, good solar. Iowa, great wind, not as good solar. Massachusetts, lousy everything. Right? Lousy everything. Massachusetts is the Germany of the United States. Great enthusiasm, right? For lousy renewable resources. Right? Okay, so that's what we did. Right? And so I'm going to give you a snapshot of what comes out of this kind of analysis. What does the battery do? And so this is Iowa wind delivering baseload, right? And this is 20 years of backwards-looking data. So most developed parts of the world, the renewable resource is available. Those data sets are available. So this is hour by hour over 20 years. You can get that data. We just have to pay a little bit of money for it. Right? And so you look back over the last 20 years, and there's the solar profile going like this. And then the wind profile does that. And so you can do one the other, or you can, so in this study, what we did was to take that, you can do one the other or both. And so the optimization is this. You're allowed to take your wind or your solar, which has a price, a cost of that technology, choose a reasonable value for the cost, and you're allowed to either expand or contract it so you can overbuild. Right? And you have a battery, has a cost of energy and a cost of power. You're allowed to expand or contract that. And you combine those two and you minimize the cost of electricity that you produce in order to meet a particular profile. Okay? So that's the process, and of course there are all the details behind how that's done. But the thing I want to point out is that if you look at this, what this battery does, I made the analogy to someone earlier today. This is like, you imagine the cell phone user who's paranoid about running out. And so what they do is they constantly top off their battery. And once in a while they forget to do that, and oh my gosh, I actually have to run it down and use the whole battery. Right? So this is like that. The deep dropouts here are when you lost both forms of renewable power, and you had to cover output for a few days. Right? And so if you expand this, what you find is that there are, over these 20 years, all these spikes downwards are on the order of a few days. Right? And so it's not a few hours, but really a few days, and that's what you're building the battery for. And in this case, you're sizing the battery for the worst extremes, which happened twice over 20 years. Right? Right? And as you can imagine, this is going to require a very low-cost battery, right? Because you're building a giant battery, lots of ripple on it, but sized because you have to. You have no way to, no other way to cover that intermittency, and you then have to deliver power at the rated profile for a few days. Right? And so if you take that kind of output, and so this paper has a 50-page appendix, by the way, so lots and lots of plots, right? And so here's just one plot, that Iowa wind example, right? And now the color scale goes as follows. Let me explain the scale. The color scale is just the cost of electricity, right? And matched up against nuclear, coal, and gas. And the horizontal axis is the storage system on a dollars per kilowatt hour basis, which is mainly how much chemicals do you need, and then the vertical scale is dollars per power, which is a different design criteria. For instance, as a flow battery, is how big the stack is, right? And then it turns out that if you can imagine, you can see how if one axis is dollars per kilowatt, the other is dollars per kilowatt hour, the slope is related to time. Right? And so the slope is how long that battery discharges for. And there you see 4 days down there, 100 hours. Right? And so what this tells us is that in order to deliver blue, low-cost electricity, right, to match natural gas, what you need is storage costs below about $30 a kilowatt hour. But this is a battery that's running for multiple days. Right? It's relatively insensitive to the cost of power. Right? And so that starts to tell you something about what type of battery you need for very high renewable penetration. Right? And there are similar results for each of the other regions. So if I try to summarize the kinds of things we're learning, the next question here is, can lithium-ion do it? And the simple answer is that lithium-ion can't do it. And it can't do it for two reasons. One is that it's too expensive. And the second is that we don't have enough of the components that go into lithium-ion to meet the storage needs. So it's a fair amount of information here. So let's first start with how do we beat natural gas? So I'm going to actually give you a very simple equation now. I have to give you the complicated version and say that natural gas today is $1,000 a kilowatt. And it's not per kilowatt hour because it's unlimited in the kilowatt hours. You just keep supplying gas to it and it keeps delivering kilowatt hours. But to build a power plant is $1,000 a kilowatt. Peakers are a little less, Peakers a little bit more, and I think CCGT is a little bit less, but it's around 1,000. And so you just do the dimensional analysis. If we're operating it over 4 hours to equal $1,000 a kilowatt, we can tolerate $250 a kilowatt hour. That's the current cost of grid-scale lithium-ion. Right? And so what that tells you is that lithium-ion is affordable today in gas peakers that can compete with natural gas. That's in fact what's happening. So the so-called emissionless peaker based on a lithium-ion battery is cost competitive with a natural gas peaker. And those kinds of things that's where the kind of deployments are taking place, right? But if you go to something like a 100-hour interval, like I showed you in the previous slides, now you need $10 a kilowatt hour. And there's a lot of analyses, we've done some of them, and $10 kilowatt hour lithium-ion is not in our future. The minerals today cost us about $25 a kilowatt hour before we've actually built the battery, right? And so you would say this multi-day storage problem is one that lithium-ion cannot solve from a cost perspective. Right? The next part of this is, well, how much will we actually need of all these batteries? And so this is a topic. So the question is, right, in a fully decarbonized world, and where we electrify as much as we can, how much battery do we need? Right? If I were to ask you that question, I wonder if anyone in this room has an answer that they would say, I know the answer to that question. Well, we didn't know the answer to that question, but we have a study going on at MIT, at the MIT Energy Initiative. It's called the Future of Storage Study. And so one of the things we've been looking at is this question. I'm going to give you a nice round answer, which is 100 terawatt hours of storage, okay? And I'll reference that against the fact that some studies today come out with the answer that just for electric transportation, we'll need 2 or 3 times that, up to 300 terawatt hours of storage. This is a more conservative answer that assumes that we don't electrify all of transportation, and we add the grid storage of the kind I just referred to. So what's 100 terawatt hours? So it's just a number. It turns out to be 1 billion high-end Tesla Model S's. Okay, 1 billion 100 kilowatt-hour EVs. Right? And so, well, how much battery is that? Well, so we can compare that to, for instance, the fact that we have the world's human population is 7.7 billion people today. By 2040, 2050, it'll probably grow to about 10 billion. Right? And so that's roughly, think of it in terms of 1 Tesla Model S pack for every 10 humans, right? And so, well, that doesn't seem crazy, right? Doesn't seem extraordinarily high, extraordinarily low, so maybe that's a reasonable answer. So this 100 terawatt hours has significant error bars on it of maybe a factor of 3, right? But let's run with that and ask the following question is how much can we do all that with lithium ion, even if the cost problem were solved? And so this table here is a little bit fuzzy, but this is Bob Jaffe and Elsa Olivetti put this together just a few weeks ago, and I told them I was going to show it, and they said, don't do that, and I said, I'm going to do it anyway. So subject to revision, but what it says is the following, 100 terawatt hours, and we're going to use, those 100 terawatt hours are going to be made up of lithium ion, and lithium ion today has different cathodes that go by the acronym NMC. Many people in this room know that. And there are different flavors of NMC that use different amounts of nickel, manganese, cobalt. There's 111, there's 62, there's 811, right? And if you look at this, if I just ask you to focus on the yellow rows for a second, right? This is for the lithium. If we take the production of lithium in the year 2018, in order to reach this 100 terawatt hours, how much does that production need to scale? And well, in the first case, we need 164. We need to scale by a factor of 164. Right? So we have to take the amount of lithium we produce in the world today, 164 times. And similar answers for the others, because the amount of lithium is relatively the same. And if you ask of the known resources, how much of the world's lithium would be consuming? Well, about 20%. That might not make you terribly nervous. If you go to cobalt in 111, well, we need 1.5 times the known reserves of cobalt, so that's a problem. Right? But we're going towards higher nickel. And so maybe cobalt, we only need 40% of the world's cobalt. We won't allow anyone to make stainless steel and a few other things. So you would need about 40% there. And on the nickel side, we might end up, if we go to high nickel and low cobalt, about 60% of the known reserves of nickel. Right? And so that's a problem because then we don't leave enough for all the other industries that today use cobalt. Right? So that's one of the reasons. So that's a long-winded answer to the question, can lithium ion do it all? And the answer is no. Right? So let's see. I'm going to need to move a little bit more quickly here. So this is a plot that I've used to show what the cost of chemicals is that goes into batteries. And on here, the blue triangles are lithium ion, different flavors of lithium ion. And the low end of that, as I said earlier, is about $25 a kilowatt hour for just the chemicals to get involved. And so if we think about this $30 kilowatt hour all in, which is roughly that bar there, almost nothing on this plot is below that bar. Right? Only a few things are. And it turns out that those few things are going to be things that are very abundant today. And our favorite today, I'll tell you, is one of our favorites today is sulfur. Right? Okay. And so, material scientists are used to having the entire periodic table to work with. And we love to build these exotic materials that use all things. Right? And already for lithium ion, we are limited to the top third or so of the periodic table. But what we're saying here is that for low-cost grid storage, we have to work with even a more restrictive menu. Right? And so some people might say, well, that doesn't seem very exciting. You have to work with cheap stuff. Everything is focused on cheap stuff. But my analogy is this. If you're cooking and you have to cook with fewer ingredients, right? Let's say all you get to use are potatoes, right? You have to be much more creative, right? And so this is not bad for material science. This is actually, we have to just be more creative and figure out how to use these very low-cost materials. And so this particular example is using sulfur. And one of the conclusions we come to is that very low-cost inorganics, and I say inorganics because that's what I know most about. And there's another world of people who focus on organics, but very low-cost inorganics in a configuration where the other electrode is air is one of these boxes of chemistries where we can get to these very low costs. Right? So very low-cost metal-air batteries would be another one. This one happens to be sulfur on one side and air on the other. I'm not going to say too much about this chemistry. You can read about it. But basically what we have here is a polysulfide solution, which is similar, so it's an aqueous polysulfide solution on the left, which is basic. And so we have sulfur undergoing redox over there. And then we have an intermediate solution, and that side is basic, this side is acidic. And so there's some challenges here in the membrane, because we have acid and base both. And the acidic side is actually exchanging with oxygen. Right? And so it's not so much a sulfur air battery, because we're not directly oxidizing, reducing the sulfur itself with oxygen, but it's air breathing, right, in this case. Right? And so this is one of the chemistries that we've been working on. And now, the interesting thing about sulfur is that 100 terawatt hours, the annual production of sulfur is roughly a quarter of that. So there actually might not be enough sulfur. Right? And especially if all our sulfur comes from natural gas from fossil fuels, which is where it comes from today. Right? So we thought this was great several years ago, and now we're thinking, maybe there's not enough sulfur in the world. Right? Okay, but it's an example of using a very low cost chemistry. And so this is Saudi Arabia. This is a giant sulfur deposit, and so this is 25 terawatt hours. And you see, just for scale, that's a pump hydro facility, and that's only 15 gigawatt hours. Right? So there's a big scaling that needs to take place. So this is the first part of what I wanted to talk about. So what do we do? What are we actually doing with this general idea? So I don't want you to. So what happens is that as a researcher, you can't work on all chemistries at all times. So we had to choose one. We worked on sulfur. Right? But what I've try to convey is that there's a box of chemistries. They all have to be based on very low cost inorganics. And probably looking at oxygen as the other reactant is a really good idea. Right? And so this is an area that I think deserves a lot more attention. In this particular case, that project started as a DOE Basic Energy Sciences funded project. And it started at a time where this question of do we need long duration storage was unanswered. Right? And so it has made its way to an RPE project now. RPE project, the project called DAYS is days, right? Beyond the hour and the day is multi-day storage. And so the existence of that RPE project, I think, is in part due to the ongoing dialogue that we had with RPE as that project was going on. And now we have a company which is about 3 years old, has about 40 employees, located in Somerville. And it's called Form Energy, and the investors include, for instance, Breakthrough Energy and Eni, it's an Italian oil company, an oil major. And so these are my co-founders there, and so I want to point out on the far left is Matteo Jaramillo, who was director of drivetrains at Tesla, and then started Tesla, the division called Tesla Energy. And when he left Tesla, he was looking for something new to do, and we were fortunate to get him involved. And so Ted Wiley, another co-founder, Billy Woodford, who was a graduate student working on that project, and then Marco Ferreira, a lot of that modeling of the use cases I showed you earlier, he is the initiator behind that work. Right? So what does this look like? Here's a pretty picture. But it also has some numbers involved here. People often ask, if you build this kind of battery, how big is it? Do you need to buy the ranch next door to the wind farm? And so it turns out that when you work through all the numbers, the power per footprint is in the range of 1 to 2 megawatts per acre, right? 1 to 2 megawatts per acre. And that's a meaningful number because that's what a natural gas power plant is today. Right? And so we have lots of space around our renewable generation facilities to do that. The other thing that this is trying to convey is that we need to be able to, in order to scale to 100 terawatt hours, we need to build batteries in a different way than we build lithium-ion batteries, which is that you build a purpose-built gigafactory for making electrodes and winding batteries. We need batteries where you can assemble them, where you can get contract manufacturers, so-called EPCs that build factories and facilities, and have them come in and just ideally assemble on site what a battery looks like. And so that's kind of the direction that this is all headed in. Can I do just a time check? How much time do I have left? Yeah. 10 minutes, okay. All right, I'm gonna keep going then. All right, so now I'm gonna, so what else can we do with renewable electricity? We can store it, use it later, right? Or we can convert something with it, and there are many things that we can convert. So this is a project that was initiated by conversations with Dave Danielson, who used to be at ARPA-E and then was heading up EERE, and then now is at Breakthrough Energy. And for a couple of years, he said, you should think about cement. Cement. I've been in the ceramics field for 40 years, and there's always been a cement division. And I never ever went to any of their meetings. I'm looking at Rudiger Diekmann here, and I bet he didn't either. So, cement has been, I have not paid attention to cement my entire career, but I am now, right? And here's the reason. So three numbers. Each kilogram of cement emits 1 kilogram of CO2. Right? Easy number to remember, 1 for 1. Secondly, we produce 4 billion tons of cement a year currently. Right? So 4 gigatons of CO2. And that adds up to 8% of global emissions. The largest CO2 emitter of any industrial, first the largest volume industrial material, and secondly the largest CO2 emitter of any industrial material. Steel is second, right? Cement is first. Right? And then 13 cents a kilogram selling price. It is utterly commoditized. Right? And so the hardest things to disrupt are those things that are completely, utterly commoditized. Right? And so one macroscopic way of looking at this problem is that finding a cheaper cement than Portland cement the way we use today is going to be really, really difficult, just flat out cheaper. But what's happening is that this industry is going to, one way or another, be charged for the CO2 emissions. So cement will get more expensive. There will be some increase in price of cement due to the CO2. And our job is to figure out how to come up with the lowest cost solution given that CO2 price. Right? So that's one way to think about it. So we don't have aspirations of actually producing cement for less than 13 cents a kilogram. Right? Right? But for maybe less than, let's say, a $50 a ton carbon tax. Right? So this is a new building at MIT. The reason I show it is because they have this beautiful limestone. Right? And this limestone is quarried in southwest China and shipped to the US, high carbon footprint. Right? But this is what we make cement out of. So cement and concrete is mankind's effort to take limestone and turn it back into limestone in a more convenient form. Right? And so cement, just to remind you or inform you if you haven't ever thought about this, so concrete is the stuff with the aggregate in it. That's the gravel. Cement is the paste that holds it all together. Right? So when I speak about cement, I'm talking about that white paste. And the term of art is ordinary Portland cement. And the thing I always say is that the word ordinary is not an adjective, but it's a noun. It's ordinary Portland cement. Right? And this is the way, so just a very simplified way of describing how it's made. We take limestone, we crush it up, we calcine it. So limestone calcined to lime, calcium oxide, that's where the phrase calcining comes from. We add silicates to it, and we produce a calcium silicate of a particular phase, which then is the so-called cementitious phase, which means that it reacts with water and forms the cement that we're after. Right? And the emissions from cement look something like this. If we take the calcium carbonate, that's half of it. It's a chemical origin. Right? The other half comes from the thermal processes, the fuel that's used today. And it's almost entirely coal, right? And so, but people throw old tires in there. They try to add other, try to use other supplemental sources. But this is how it breaks down. And so we need to do something about, I would say, both of these. But if you can do a lot about any one of them, it's a big dent. Here's another number. Current production of cement is equivalent to building a new New York City every 30 days. Okay. And there's also a number for the cubic volume. It's huge, right? Right? It's and something like 10 miles cubed or something like that. Right? And this is going to go on for decades. All right, I'm going to move quickly. So people haven't been ignoring this problem entirely. There have been. So, for instance, you can take the CO2 as it comes out of the furnace, and you can try to capture it. There are projects like on that, right? There are projects where, or approaches where you try to put more CO2 back in the cement. number of issues associated with that. CarbonCure is a company that today works with cement producers, someone producing so-called ready mix that goes into a cement truck, and they pump some CO2 in there, and they form some calcium carbonate, but they have to deliver that CO2, by the way. And it turns out to be less than 1% of CO2 in there. So there's not a lot being captured there. Blue Planet, these are calcium carbonate marbles. They're gravel coated with calcium carbonate. Another way to put more. So this is on the tail end, right? That's capturing the middle. And there have been a couple of attempts to, Solidia also uses CO2, tries to capture more CO2 in the cement product. Calera is one of the first generation clean tech companies that tried to find an electrochemical process to make a different different cement compound that would go into cement. Right? So when we looked at this, we said, okay, number one, getting people to adopt a new type of cement other than Portland cement is going to be difficult. Not when it's produced at 4 billion tons a year and at 13 cents a kilogram. Right? And we have lessons where a new compound adoption is difficult. It has its issues. Go for it. This should go on. Right? People should try to do CCN cement flue gas. Right? Well, there are people trying this. You have to see how much you can actually capture. Right? So what we say is there a way to just use renewable electricity? And now, can we make Portland cement a different way using low-cost renewable electricity? Right? And so this is a figure, and as any of you have read our PNAS paper, you'll know what we're showing here, but I want to point out something. It's a simple H cell, so obviously it is an electrochemical cell of some kind, and part of the hint is that there's a gas bubble. There are gas bubbles, both electrodes being evolved. And then on the horizontal scale is a pH scale, and it turns out that there are a few drops of pH indicator in this solution. And it's a very simple neutral water electrolyzer, right? All it is generating, so this is the basic end, so OH is being produced here, which means hydrogen is being evolved. The acidic end, oxygen is being involved and is turning acidic. And so this is the part of the electrolyzer that many of us forget about. It doesn't just produce hydrogen and oxygen. It also produces acid and base. Right? And so our basic idea here is that an electrolytic process, not only this one, but ones like it, it's auto-advancing now, will produce an acid stream and a base stream. And we're going to use that acid and base in order to carry out a chemical conversion process. Right? And the conversion process is very simple. Right? We have acid here, and base there, I think I just talked about that. And now imagine if we drop calcium carbonate in the acid. Right? What happens is that it dissolves and CO2 comes out. Pure, clean, room temperature CO2. Right? Not dilute, hot, dirty CO2 in a flue gas. And so pure, clean CO2 actually has value. And you can simply compress it. Right? Dry ice, beer, soda, and a few other things. Actually, a lot of it can be used for enhanced oil recovery today. Right? So the idea was to liberate this clean gas. It's mixed with oxygen, but we can separate those two pretty easily just by compression too. And then the dissolution of the calcium carbonate, and these calcium ions, upon meeting the base on the other side, will simply produce calcium hydroxide. And so here's a precipitate. Right? And so we produce a compound called hydrated lime, which it turns out has a higher market value today than cement itself. Right? But it can also be used to make cement. When we discovered that it has a higher market value than cement itself, well, gee, maybe we want to stop right there. Stop right there and go sell that stuff, right? But the long-term idea is to produce cement, right? And so in this reactor, what's happening is that we just simply put a piece of filter paper in the middle and we collect the calcium hydroxide as it goes. It's a very, very rudimentary reactor, right? I hesitate to even call it a reactor, and I'm talking to a chemical engineering department, and you're not liking that, I know, right? But we're getting chemical engineers involved to build real reactors now, and so it turns out that this is beautiful pure calcium hydroxide, which then we can go ahead and make. Here's more of it, and well, what do you need to make? calcium hydroxide, and this is just a laboratory experiment, mixed with silica and now heat treated, and we get A-light, which is this tricalcium silicate, which is the primary active phase in cement. And so at this point we say, oh, proof of concept, we can make cement. And all the cement chemists say, no, you haven't made cement. Cement is much more complicated than you understand. And we say, yes, we know that, right? But it's on the way to making cement, right? And so unfortunately, this heat treatment still has to take place at 1500 degrees C because the phase A-light is only stable, thermodynamically stable above about 1450, right? So, okay, I'm going to wrap up. One of the interesting things about this process is that it's naturally purifying because we dissolve the calcium carbonate and all the impurities settle out, and so we get this high purity stuff, which is why we think that there's some other applications for this. And I'm going to close with the last question. People ask, so is this really scalable? Right? Can you really, you show me this H cell? I mean, yeah, and you're going to go from that to 4 gigatons a year? Yeah, give me a break. And so what we do here is that we reference other large-scale electrochemical processes. Right? And these are some of the world's largest electrolyzers today. And so if you take one of these units, you can produce about 30,000 tons a year of this lime that would go into a cement plant. So that's one scale, but I haven't told you what a typical plant produces today, cement plant. So a typical plant might produce a megaton of a year of cement, right? And so to do that, we would need about 200 megawatts of power going to it. Right? So is that a lot or a little? Right? Well, it turns out that an aluminum smelter consumes far more than that, and we have lots of those around. Right? And so large-scale electrical processes exist. Large-scale electrochemical processes are a little bit smaller, but we think that there's evidence that this is ultimately scalable. And the final part, I'm just going to say, here's a scheme for this is one part of what you might imagine in the future. So very low cost renewable electricity. It's intermittent. In this case, we can deal with the intermittency because we produce an acid and a base stream. We just store that, right? Plastic tanks, low-cost steel tanks. We produce lime or cement at the rate we want to. And then we have, in this case, hydrogen, oxygen, and CO2. And those are the feedstocks for a whole bunch of other processes that many of you know about, right? And so you can kind of imagine this. And then how much additional energy do you need to add to the system? Well, it turns out that the calculation shows that if we take the hydrogen out of this process, operating this reactor at stoichiometric, under stoichiometric conditions, that hydrogen is just about enough energy to complete the firing process. So it's actually possible to imagine a cement plant that operates solely on renewable electricity. Okay? So I'm going to stop there. I am probably over time a little bit. Thank you for your attention. I'd be happy to answer questions and we have time.
So we've got time for a couple quick questions, but I want to remind you there's room upstairs. There's lots of good food. So if you don't get your question answered, come up to room 216 in the building. So any burning questions for now?
I'll save one.
Yes.
Thanks, Jeff.
Do you really think that electrochemical batteries are the way to go instead of storing hydropower and stuff like that?
Yeah, very good question. So really, when it comes to storage, all options are on the table. The big thing that electrochemistry has going for it is that even a lousy electrochemistry has at least 100 to 500 times the energy density of mechanical storage. Right? And so, of course, pump hydro requires the right geological facilities. My joke is that the ultimate winning technology is pump mercury. Right? But until we have that, electrochemistry is still a pretty good bet. Yeah.
What's the largest, scale-up you've done so far on this hydrolysis for cement production? You showed a small video of what you've done in your lab.
Yeah.
Have you done any scale-up beyond?
No. So we are literally at that building. So there's something a little bit beyond that. But I'm getting together. We need I now have a chemical engineering graduate student involved, and yeah, we have to take the next step. But what we're actually spending a lot of time doing is visiting commercial plants of the kind that I showed you to kind of get an idea of what the future would have to look like, and then we're going to go back to the lab. Yeah.
All right, good. So thanks. Yeah, thank you so much, and thank you guys for coming.